Okay, so let's get started with this warm-up. So for the warm-up, we want to find the component form and magnitude of the vector v that has its initial point p at -2, 3, and its terminal point q at -7, 9. So real quick, I'm going to just, I didn't ask you to do this, so if you didn't, that's okay. So I'm going to sketch it out, and I'm going to show you with the graph. If I cannot draw a straight line. What's going on? All right, that's as straight as we're going to get. That one was so much better. All right, so my initial point P is at -2, 3. So these are just going to be rough sketches. And then Q is at -7, 9. So maybe somewhere like up here. All right, and then the way it's going to point, so this is my initial point, so this is where we start, and that is not going to there. I'm having such a hard time today. All right, so there is our vector. A really crappy drawing, but there's our vector. All right, so first, for the component form. All right, so remember our component form only involves two coordinates, v1 and v2. So we want to make the p and the q into this. So to do that, we are going to subtract. And it is going to be, let me make sure I have it right. Yeah. Q1 minus P1, and then Q2 minus P2. Right, so we would start with the, wait, did I set this up right? Yeah. So I'm going to have -7 minus -2. All right, just be careful with your signs. And then we're going to have 9 minus 3. And we just simplify. This becomes plus. So this is -5, and this is 6. Right. So this is my component form, -5, 6. Which means if I wanted to move this so that its initial point was at the origin, these would be the coordinates that would give me the same exact line. So -5, 6. And then come up this way. Oh my goodness. I'm having such a hard time drawing lines today. I'll make it green. All right, so there is our component form. So again, I might have mentioned this last week. It's kind of like our translation when you're talking about geometry and transformations, right? All I'm doing is I'm shifting this line. It's not changing its size. It's not changing the direction it's pointing in. I'm just moving it so that initial point we start at the origin. Now the magnitude, remember we show with the two lines. The magnitude's a lot easier to calculate when we have the vector form. Okay, we take the square root of the sum of the squares of my component form. So whatever your coordinates are there, you're going to square them and add them together. Now, 5 squared gets us positive 25. Be careful. If you're plugging that into the calculator, make sure you don't get negative 25. And then 36. So we add them up together and we get the square root of 61. And remember, we're going to leave it just like that. We don't have to calculate. All right, so I have the component form here. And I have my magnitude here. All right, any questions about that? That's what we did last week. Okay, so today we're going to talk about vector operations. There was the one question, I think it was, I forget what number, it was maybe 5 or 6 or 7. It did involve something called a dot product. I'm not sure if we'll be able to get to it today, but if not today, then definitely tomorrow. So for vector operations, we can perform some mathematical operations on our vectors. Before we get too fancy with what's called scalar multiplication, we have some very basic ones. We have vector addition, and then we have something called scalar multiplication. Okay, with vector addition, just a rough sketch. So say I have two vectors. I got v here, and then I got maybe u going this way. With vector addition, what we do is we move one of our vectors. Can I do it? Oh no. Try to be fancy, but it's not working. So I would move one of my vectors, in this case, maybe the u vector, so that this endpoint, or this initial point, matches up with this endpoint here. So I'd move this u over this way. All right, so that would be my u. So the resulting direction, so from here to where u ends up, well, that would be my addition. This here would be my u plus v, or v plus u. Okay, or you can look at it the other way. If I took my v and then I move that, so it's at the end of my u, and again I added them together. Okay, it may not be in the same spot, but these sure look like they have the same direction and they have the same magnitude. They're going to have the same length. This would be my v up here. All right, so that's a graphical explanation of vector addition. It might be a little easier when we're looking at it numerically. So we have our v vector, v1 and v2. And we're going to have our u vector, u1 and u2. So we're just going to be adding the respective parts. So I would add my u1 and my v1 together for the first point, and then I'd add my u2 and my v2 together. Then we have something called scalar multiplication. Oh, well, so side note, vector addition is kind of like we said before, it's kind of like translating if you want to tie it to geometry, right? So how would I translate moving in a v vector and then moving in a u vector afterwards? Okay, so remember, vectors are used to describe things like projectile motion. Okay, they're used for real life things that have not only a factor to them, a magnitude, like miles per hour, or for, you know, like maybe acceleration, so feet per second squared. But also the direction part, right? So that's what we get when we So, when we were talking about bearings, right? So if I'm traveling northwest for this much, and then I turn and I go, I'm sorry, northeast this much, and then I turn and I go northwest this much, well, then I can just say that in general, I went northeast, maybe not as far as that way, but a little this way, and you can see that they added up together there. All right. But mathematically, it's pretty straightforward. You just add the x coordinate, and then you add the y coordinate. Scalar multiplication is like dilation. All right, so say I have some vector here, some vector v. And now what I do is I multiply this by some constant. So maybe I multiply it by 2, right? So if I multiplied it by 2, it'd go in the same direction. It would just be twice the length. Okay, if I multiplied it by half, it would go in the same direction, but it'd just be half the length. Okay, I can make it negative. If I say negative v, that means I go in the opposite direction. All right, so that's what scalar multiple is. So again, we're going to have some vector. Okay, I'm going to call it u here. Okay, so if I'm multiplying by a scalar multiple, then I'm just going to take my vector coordinates and I'm going to multiply them by whatever that scalar multiple is. And so if this was, 5, 2, and I doubled it, it would be 10, 4. I would just multiply everything by 2. So we can combine these two to give us subtraction. All right, so before we jump into some examples, okay, so if we have some vector v and we take the negative of it, well, that's doing a scalar multiplication of -1. So that would give me my, opposite coordinates, which is what we saw up here when I did the green line. All right, so we have the same starting point. I'm just flipping where the coordinates go to the other side. Okay, so excuse me, it's like a reflection. So if I take that into consideration, then I can say the difference of two vectors, u and v, if I had u minus v, okay, that would be the same as u plus -v. All right, so now normally when we do, basic algebra or arithmetic, technically this is what we're doing when we're subtracting numbers. I'm adding the negative component. But when we're doing it normally, we don't have to write it like this because it kind of just works out in our head. But now that we're dealing with vectors and different quantities and they have different components to them, okay, this is kind of how we look at it. U minus v is the same as u plus -v. Right? And that would give us u1 minus v1 and u2 minus v2. Okay. And again, remember, I keep forgetting, but anytime we're talking about vectors, we use the triangular brackets here. Okay, so make sure you have those triangular brackets. Okay, I think, yeah, we got some time. Let's look at some examples. Um, all right, so let's take a look at a few things here. We have two vectors, -2, 5, and 3, 4. So I'm going to do the math, and then I'll also graph it out so you can see it visually as well. So the first thing we want to do is find 2v. So I want to find the scalar multiple of my vector v. Right? So 2v, to write it out mathematically, 2 times, actually let me do 2 times my first, -2, and then 2 times my second part, 5. So 2v would be -4, 10. All right, I think that's pretty straightforward. So yeah, so if I graphed it, -2, 5. Let me go here. All right, this would be my original v. And then multiplying it by 2, I'd go to -4, 10. All right, and this is just a sketch, but that looks pretty close to twice the length of my vector v. Again, it's going in the same direction. I'm not changing anything about the slope. I'm just making it larger with the scalar multiple of 2. All right, u minus v. So if you're comfortable with dealing it like this, okay, you don't have to rewrite it as u plus -v, all right, but just know that that's how it is. So here, u minus v. So I'm subtracting. Just make sure you're careful which one comes first. All right, my u vector is first. I'm going to have 3 minus -2. And then I'm going to have 4 minus 5. So 3 minus -2 becomes 5. 4 minus 5 becomes -1. So I have 5, -1. So I do want to look at this because we didn't talk about subtraction with the graphs. I may have to move this. Let me just do this real quick. Yeah, let's copy it. All right, so let's take a look at this on the graph. Nope, it's not doing it. 5, 2, 4. All right, so I have my v again, so that's this is crappy. -2, 5. Sorry for being all sloppy here. Actually, let me fix this. Nope. I wish there was a way just to make a straight line. I make circles and triangles when I don't want circles and triangles, but I can't get a straight line. All right, so I got my v vector here at -2, 5. I have my u vector here at 3, 4. So now I'm subtracting these two, okay? So I want to end up at 5, -1. So normally, again, I would move my v to the end of u, and I'd have, a line that looks like this. But that would be addition. I'm subtracting v. So what that means is I have to take my v, and because I have the negative in front, I'm changing its direction to down. So this over here would be minus v. And then my result would be that u minus v there, okay? So if I was just adding, again, I'd have the v, I'd move that to the top here, and I'd be somewhere, I'd be at 1, 9. So that'd be like, really tall up here. But because I'm subtracting v, I flip the vector around. So it's, a mirror image, it's a reflection. And then I can add it onto the u. All right. Okay, I will say this, if this part confuses you where, it's the graph part, just worry about the math part. All right, and the last one I do want to show you quickly. Hopefully it works. Can I just? It's nice. Okay. So here, v plus 2u. Okay, we gotta do it in 2 steps. First, I have to figure out what is 2u. All right, so I'm doing a scalar multiplication on u. So I'll do that first. So multiplying u by 2, I'm going to get 6, 8. All right, so now I'm using v, and I'm adding to that my new vector, 6, 8. So I'm going to have -2 plus 6, right? My v plus my new u. And then I'm going to have 5 plus 8. Which is going to get me 4, 13. And quickly, again, here's my v. Was it -2, 5? My u normally would have been here. This is v. This is my normal u, but again, I'm multiplying it by 2, so I'm ending up at 6, 8, right? And now I'm taking this, and I'm moving it on top here. And so this line here, which is the addition of v plus 2u, leaves me at 413. All right, and that just takes us right to 11 o'clock. So tomorrow, we'll talk about the last part of vector operation, which is scalar, which is called the dot product, dot. And with that, you'll be able to answer that one question on the Otis, on the SGO. Okay, so quickly, I know we're out of time. Give me a second.